Hi, everyone, and welcome to this session about data science in Microsoft Fabric. My name is Nellie Gustafsson.
And my name is Misha Desai.
I'm Eren Orbey, and we're product managers on the Synapse data science team in Microsoft Fabric.
And today we're excited to tell you about some of the new data science capabilities in Microsoft Fabric.
Let's get started. You may have already heard about Microsoft Fabric. A quick recap is that Fabric is our new data platform for all analytics workloads and integrates Power BI, Data Factory, and the next generation of Synapse with completely serverless, easy-to-use experiences for a variety of roles, including data science practitioners. In this session, we will focus on the data science workload in Fabric. Before we get started covering features and demos, let's quickly touch base on why data science in Fabric is valuable. First of all, Fabric is data-centric. You manage your data in Microsoft Fabric, so all the data assets like, for example, lakehouses are here, as well as your Power BI datasets. In Fabric, data science practitioners can now work seamlessly on top of the same secured and governed data. And the Open Delta Lakes support enables reproducibility for machine learning. Fabric is also developer-friendly. Easy-to-use experiences on top of our serverless infrastructure allows developers to get started quickly. You get code authoring experiences in notebooks and an integration with popular tools like VS Code. We also offer rich and scalable ML for the full data science lifecycle. With built-in ML flow model and experiment tracking, we allow data science users to version and manage their ML artifacts using standard ML flow APIs. And with ML flow autologging, we make it super easy for users to automatically track key parameters and metrics during model training. And we've also developed a large set of built-in scalable ML tools with our Synapse ML library. We'll cover all of this and more in a bit. And last but not least, one of the key advantages of a unified analytics platform for all analytics roles, including data scientists, is easier collaboration. Our users can leverage the same set of tools and integrations regardless of whether they're working on data engineering, data science, or other BI and analytics tasks. This makes it easier to securely share data, code, models, and experiments across teams. Now, let's take a look at how the Fabric data science capabilities fit into the data science process. The data science process is an iterative process and typically starts with wanting to answer a question. For example, questions like, which customers will churn in the coming month? This is a step where data scientists need to collaborate with stakeholders like analysts and business users. In Microsoft Fabric, this collaboration is much easier since stakeholders who work in Power BI and analyze the data can seamlessly share reports and underlying datasets with data scientists. And with some added capabilities using semantic link, which you will hear about a bit later, data science users can now tap into the semantic data layer. Additionally, data engineering teams have prepared lakehouses that can be shared. Microsoft Fabric makes these handoffs easier. Data scientists can use notebooks to author code and explore and prepare data. And we've also added low-code tools like Data Wrangler, which data scientists can use to speed up the tedious steps of data cleansing and preparation. And once the data is in a good shape, you can start defining features for the ML model training. Thanks to the built-in ML flow capabilities, experimentation can easily be done with standard ML flow APIs. And with added support for autologging, metrics are automatically captured. The rich Synapse ML library also provides a large variety of easy-to-use ML tools for distributed and scalable ML on Spark. Throughout this process, there's a constant need for communication between data science users and stakeholders. Again, thanks to Microsoft Fabric being a unified platform for the various roles involved in an analytics project, sharing insights and collaborating is very seamless. And once the best machine learning model has been evaluated and approved for deployment, the scalable Spark predict function helps you score large batches of predictions. There are multiple ways in which automation can happen. You can schedule individual notebooks to run on a regular basis, as new data lands in a lakehouse, for example, or you can run notebooks and Spark jobs as part of data pipeline activities. The predicted values can then be stored in lakehouses in Delta files. This makes the serving to Power BI very simple with the Power BI Direct Lake functionality. And as new data is scored, new predicted values are automatically available in reports so that analysts and business users can consume them. Now I'm going to hand off to Misha, who's going to cover some of the model training experiences in Fabric in more detail. Over to you, Misha.
In this demo, we'll see how we can use Fabric to track the development of a churn prediction model. Now, the first thing I want to do is I want to install IMVLearn. This Python module helps in balancing datasets which are highly skewed or biased towards some classes. Now, one of the things I'd like to call out here is how we're using these session scope libraries for our ad hoc analysis. While public libraries can be loaded at the workspace level, users can also customize their sessions using the inline pip-in conda installs. And what this does is that it makes these libraries available on all the nodes so that I can use it for distributed calculations. The other thing is that I don't need to worry about other users using the same capacity. These changes are isolated for my session, and so this makes it particularly useful for collaboration and rapid iteration for data scientists. Now, for our analysis, we'll read the data with Spark and train several different machine learning models. These models will be analyzed within the notebook and tracked using MLflow. And so we'll take our first step and we'll take a look at our data. Our data set contains the churn status of 10,000 customers and includes attributes with their credit score, location, age, tenure, whether they're an active member of the bank or not. And so in this analysis, we'll later see how our data set is highly imbalanced. And the challenge that we see with these imbalanced classification problems is that there's often too few samples of our minority class for the model to effectively learn. And so we'll also see how we can apply some special techniques to synthesize new samples for the minority class. Now first, we'll start by reading the data from Lakehouse. Now within Fabric, you can also use Pandas or Spark to do your exploratory data analysis and model training. And so in this example, as we go through our exploratory data steps, we'll see how we can create a Pandas data frame and do our training workflow. After we load our training data, we can then use the built-in display tools to do some basic analysis over the distribution of our data or even view the data itself. And so here I'm going to click our exited attribute, and we can then see the distribution of this field within our data. And what we can see is that even here, our data is highly skewed towards customers that have not left the bank. And so we don't have a lot of examples where customers have churned. Now, before I head into my model training process, I need to first clean and prepare my data. So to clean the data, I'm going to drop rows with missing columns or missing data across all of these different columns. I'll then also drop rows which have duplicates based on the row number and customer ID. I'll also drop other columns that I don't need to feed into my training workflow. I'll then also add some other variables to track my target attributes, the values that will be categorical and numerical, and I'll see how I can use this later in my exploratory workflow. And so now we can transition over and we can actually start exploring our data using some of the built-in libraries within the Fabric runtime. And so here we'll explore and generate some different plots with Seaborn. So now let's explore our data. The first thing we'll take a look at is the distribution of our various numerical variables. And so here we can use Seaborn's built-in box plots or histograms to understand the distribution of these attributes. We can see that we have customers whose age is over 60 and other customers whose credit score is below 400. And so what we can see from these different plots is that all of these different ranges or customers outside of these distributions can't be considered outliers. We can also take a look at the distribution of our exited versus non-exited customers and look at how our different categorical variables are distributed as well. And so from here, we can see that most of our customers are coming from France when compared to Spain and Germany. We can also see that Spain has the lowest churn rate compared against France and Germany. It's pretty interesting. Also, we see that most of our customers have credit cards, and very few customers have more than 2 of the bank's products. We can also look at these different distributions to understand that customers who are not active have often a higher churn rate, and that we also see that things like gender and tenure years don't seem to have an impact on our customers' decision to close the bank account. Now that we understand the relationships that exist within our data, we'll then perform feature engineering to generate new attributes that can be fed into our training process. Once we've featureized our dataset, we'll then create a delta table so that it can later be reused among other data scientists or even reused for other training processes. Now let's start our training process. Here, we'll experiment with a few different variations of the scikit-learn, random forest, and light-GBM models. We'll start by preparing our test and training data sets, and then we'll use MLflow to organize these various trials as runs within a machine learning experiment. Now, MLflow, in case some of you aren't aware, is an open source platform that allows data scientists to manage the ML lifecycle. If I'm a data scientist, this allows me to track the development of my model, and it also allows me to then group these various iterations within an experiment or related artifact for easier collaboration. And so we'll see a bit more on what this looks like in a bit. Now, one of the ways we've also deeply integrated MLflow into the Fabric experience is through autologging, which we've highlighted here. Now, the way that autologging has been integrated is that it allows data scientists to automatically capture the various values of input parameters and output metrics of a machine learning model as it's being trained. And so this information is then logged to your workspace where it can be accessed and visualized either using the MLflow APIs, which you can use in the notebook, or also through the corresponding experiment artifact that we've shown here in your workspace. In some cases, if you don't want to have these attributes automatically logged, you can disable it at the workspace level or even at the notebook level and manually log all the details that you want yourself. Now, in this example, what we'll see is how we can use MLflow and autologging in our training workflow. Now, to do this, I'll generate a new training data set, which includes synthesized examples or new samples to represent our minority class. We'll then create a new MLflow run using the random forest classifier. And so here what you've seen is we've passed a specific set of parameters to feed this particular classifier, and then we'll fit it to our training data set. Now, the other thing I want to highlight here is that the code you see is no different than, if you were to write and train your own machine learning models without MLflow. The only kind of difference that you've added is a wrapper basically to let MLflow know that, hey, I'm starting a new run. We'll also repeat these steps for other classifiers that we might want to train. And so here we'll try a different set of parameters, and we'll also train a separate light GBM model. And so again, from the code, you can see that I don't manually or specifically specify the parameters, metrics, and properties. With autologging, each framework will automatically capture certain parameters, metrics, model details, and log these attributes automatically. The benefit of this is it allows data scientists to focus on their model training process without spending a lot of additional code or a lot of additional effort to log all these other details. Now, all of these different artifacts and these different metadatas, they show up in what we call an experiment artifact within Fabric. And one of the most common pieces of feedback that we've heard about the data science workflow is that it's challenging to be productive. And some of these challenges that data scientists face is specifically around how all these different trials get organized and how they get tracked as an experiment. And some of the challenges or things that we've heard from data scientists on this are things like, how do you know which data or code parameters went into getting a particular result? How do you capture the whole environment if I want to retrain or get the same result again? And how do I even share the results of these different trials and combinations that I'm running with other users to collaborate more effectively? And so what you'll see in Fabric is that experiments are the main unit of collaboration for this iterative model development process. As I mentioned earlier, experiments are a collection of related MLflow runs. And so let's jump into an experiment to see how these interactions work in Fabric. Now, experiments are collections of related MLflow runs, and each run represents a combination of properties, metrics, parameters, and schema details so that I can see how this model was generated. And each run here is generated by executing some data science code. For each run, I can also examine metadata, including the source notebook, which produced this run, as well as who created the run and when it was created. I can also browse model files that we see here. When I click things like the conda YAML file, I can see the underlying environment that was used and that I could then reuse to reproduce this model in other places. I can also view plots that were automatically generated from autologging. And so here I can see the confusion matrix, or I can also view things like the training ROC curve. And these are things that were automatically captured by my autologging process. In addition, I can also browse across other runs and view things like their model properties and their details as well. Now, if I have multiple runs, in some cases, I also might want to be able to navigate to a list view to visually compare all of these different runs. And so let's take a look at how we can do that. Now, in some cases, I might have multiple runs. And so for this scenario, I can navigate to the run list view to visually compare across all of these runs. Here, I can customize the views that appear in this run list. And so in this case, let's say I don't really care about these following parameters, but I am interested in looking at things like the max depth and the source notebook. Here, I can use the customized columns to easily compare across all of these different runs. Then I can switch over to the filters view and actually sort among all of these runs and use the same kind of views that I might see in things like Power BI. And so here, I might only be interested in things where the status has been completed. Now I can select across all of these runs and visually compare them using some of the built-in tools. And so by default, some of these visualizations might not be useful. And so here I can go ahead and I can customize these views and select things that might be interesting for me to look at. And so in this case, maybe I'm interested in looking at comparing the max depth versus training F1 score. And one of the things I'd like to highlight when I go through the graph will be the run name. We'll name this graph, and we'll change this to a scatter plot. And so here I can easily view the relationship between various parameters that might exist, as well as the overall function scores that I see in my results. Now in this case, I might be interested in looking at the best model. And from this view, I might say that the best model is this RFC2 SM test 2. And so here I can go back to this view and select the model. And from here, one of the things I can do is register this run as a model. Now I have two options here. The model artifact allows me to compare across various iterations of the model. And so this is particularly useful if you have multiple models that were generated for, say, potential deployment, or if you have flows that retrain the model and then validate it before deployment. And so here, what I'm going to do is I'm going to save this as a model, and I'm going to select an existing model that I've already created. And so I'm going to add this run as another version to my churn model. And so now let's navigate over to our churn model and explore what this looks like. And so from this view, I have a few different options. I can navigate and browse all of the versions that I've added to this model so far. So if I refresh, I should see the new version that's just been added. Now, like runs, users can examine the various metrics and parameters tied to a model version. Users can also navigate to the model list view, and here they can do an easy comparison across various model metrics that might have existed over time. And so in this case, I can do things like updating the views or selecting, say, other variables that might be interested in viewing. Now, when I go back to our model details view, I can also go back and look at the underlying model files that exist for my model version, and then later use these for deployment. And the last thing I wanted to highlight here is that MLflow offers a convention for packaging these machine learning models into multiple flavors. And this aids in the deployment, which is built into the Fabric workflow. And so I'll pass it off to Eren to share more about how these models can then be applied through code and deployed to generate your predictions.
Thanks, Misha. So now that she's trained that model and registered it to the workspace, I can go and take a look at the shared artifact and use it for generating predictions, even if I didn't train it myself. I'm going to go ahead and click on Churn Model, and we're going to see all of those metrics, the information that was logged by MLflow during the training process. There's the schema, parameters, metadata, showing the versions, the time the model was modified, who created it, and so forth. I can also take a look at the underlying files of different model versions. In this case, I might head over to version 4. Maybe Misha's told me that that's the version to use to generate predictions. From this apply model prompt, I can do two things. Either I can launch a wizard that will walk me through steps for selecting input data, mapping columns from that input data to my model, and choosing a destination location for predictions, all without writing code. This is a useful flow for newer data scientists, citizen data scientists, or Fabric users who might just not be as familiar with the Predict API that we have. Alternately, from that same prompt, we can copy a code template to apply the model and generate batch predictions code first. For now, though, I'm going to head back to the workspace and open this generate churn batch predictions notebook to get started with Predict. Fabric's predict function supports any Fabric model that's been registered in the MLflow format. So in this case, we'll use version 4 of that churn model to generate predictions on our test data. First, we're going to load test data from the lakehouse into a Spark data frame. We're going to create an MLflow transformer to generate batch predictions, and then we'll call predict with one of 3 APIs for maximum flexibility. Here, I'm loading test data that was stored in our lakehouse during training back into a Spark data frame. So I can open the Lakehouse Explorer, copy the path to that table, and fill it in here in the cell in order to read that data into a Spark data frame. Once I run the cell, I can use our display function and see that all of our feature columns are here. So everything the model needs to generate predictions. But of course, at the end, the prediction values aren't there, and that's where predict comes in. Next, I'm going to instantiate this MLflow transformer object for generating batch predictions. I need a model name, a version, a name for the new column where the predictions will go, and all of those input columns. This might look familiar. If you remember on that model artifact page, you can actually copy a code template that is going to have pre-populated values for much of this. But back in the notebook, once I run my cell with those values, we have the MLflow transformer all set up and instantiated for predictions, and we can call predict with one of 3 APIs. The simplest way is with the transformer API, model.transform. Here we're going to save those predictions to a data frame and use the display command to show them. Again, we're seeing all the feature columns from our test data a few cells above, but now at the end, appended to them, we have predictions. So that's it. Ta-da! You can also invoke this predict function with other APIs. So below, I'm using the Spark SQL API, changing some parameters as I've demonstrated in this cell. Here we're showing just the predictions, not the features appended to them. You can also call predict with a user-defined function. So in this cell, that's what I'm doing, and the output's going to be the same as it was a few cells up. I'm displaying the test data frame with those prediction values attached. The last thing I'm going to do is write our predictions back to the lakehouse. Once we do that and we have predictions stored as a table, we can take advantage of features in Fabric like auto-generated Power BI datasets to create reports, to dive in deeper, and to share our findings. That's really one of many benefits of this integrated approach. Once I've written these predictions to the lakehouse, I'm going to head back up to this Lakehouse Explorer and actually refresh my tables list. And what you're going to see is we now have a predictions table there. If I head back to the workspace, I can then go ahead and click on this customer churn Lakehouse dataset that's been auto-generated. I can see the tables in it. I have the option to share that dataset with some of my coworkers, and I can also go ahead and create reports. Ta-da! So that's how we've gone ahead and enriched some of our data using model prediction capabilities, and then brought it back seamlessly, really, into Power BI, where we can share the business insights with others in our organization and beyond it. So just as a bit of a recap of what we've seen, Misha started by walking through the process for training our model. She imported some data, she cleaned it, she showed off the built-in Fabric integration with MLflow and our experiment tracking functionality to settle on the best version for making predictions. Then I took that model that she trained and used it to enrich existing data with those predictions. I showed how easy it was to serve that enriched data to Power BI so that you could build dashboards on top of it and share insights across the business. Next, I wanted to talk about a feature that we've introduced in Fabric called Data Wrangler. Data Wrangler speaks to the commitment that we've made to making data science a more accessible and open process for different personas, citizen data scientists, team members with different ranges of experience. Let's take a look at a demo. Fabric Data Science has features built in that are designed to facilitate the machine learning lifecycle for everyone, but also to make it easier for newer users, for citizen data scientists, to contribute to that process. So let's take data cleaning as an example. If I wanted to recreate those data cleaning steps from the original training notebook, but I was newer to Python, maybe still learning, maybe rusty, there's a way for me to do that. I can use a feature available in notebooks called Data Wrangler. It offers this immersive, grid-like environment with a common set of data cleaning transformations. Each of them can be applied in a matter of clicks, but the key is that they generate code, so you end up with the same result. Let me show you what I mean. I'm going to head over to this Explore and Transform Churn Data notebook. Now, our goal is to accelerate data prep using this Data Wrangler feature. In particular, we want to use Data Wrangler to recreate the cleaning steps from our training notebook. We need to drop some rows with missing data. We need to drop rows with duplicate values. We need to drop some columns entirely. We also might want to perform more sophisticated operations like one-hot encoding. We can do all that in a matter of clicks, generating code in real time along the way, even if we aren't experts in Python. To show you, I'm going to head to our Lakehouse Explorer, click on the Files section, and grab that same raw churn data as a CSV. Using the UI, I can load that CSV into a Pandas data frame, run this cell, and get a preview in the notebook with the display function. If I want to open this data frame in Data Wrangler, all I need to do is head up to the Data tab in the Notebook ribbon, click on the launch prompt for the feature, and then from a dropdown of my active data frames, select the one I want. Right away, you're going to notice some things. We have quick insights and histograms built into column headers. We have a summary panel on the right with information about dimensions and missing values. And we have our operations library on the left. Applying any of these is going to update the grid, give you the code, and then allow you to add it to that list of cleaning steps at the bottom left. The code appears below the grid. Let's start with the first step that we'd done in that original notebook. We're going to drop rows with missing values across any of our target columns. So I'm going to select all of them in that operations pane. I'm going to get the preview in the grid. I get the code generated below it, and I can apply that code, committing it to the series of steps at left. Next, we're going to go ahead and drop rows that have duplicate values across certain target columns. As we did in the original notebook, I'm going to choose row number and customer ID. The grid updates, I get the code below it, and I can apply that step again to the running list that I have at the left. I can also apply operations directly from a column. So in this case, I want to drop row number. Same deal. Preview, apply the code, get it added. If I want to apply that drop column step to multiple columns at once, I can do it from the operations pane too. And here I'm selecting customer ID and surname to drop both at the same time. Neither of them is going to be useful for a model. So let's go ahead and get rid of them and commit that code again. Lastly, I'm going to do some one-hot encoding to just give you an example of the more interesting steps that Data Wrangler can accomplish. So in this case, as in our original set of cleaning operations in the first notebook, I'm going to turn the geography and the gender categorical columns into these new columns that have zeros and ones so that I can take advantage of these features while training. Once I see that those columns look right, I can apply the code that has been generated below the grid, and that gets added to my cleaning steps too. At any point, if I decide that the most recent step I've added isn't quite right or isn't what I want, I can delete it. I can also save this grid as a CSV, copy the code to the clipboard, or add it to my notebook. And when I do, I get this focused cell that wraps up all those steps I've completed into a function. I can apply that function to the original data frame, and what I get is a cleaned data frame. But crucially, the code comes with it. So I've ended up in the same place as I was in that original notebook, but I've done it in a different way, and hopefully in a way that's friendlier and more accessible to citizen data scientists, so that team members across roles and levels of experience can all collaborate in Fabric at once. For now, I'm going to hand it off to Nellie to discuss our support for the R programming language and also to tell you more about what to expect from our roadmap. Thanks so much.
Thanks, Eren. Microsoft Fabric also offers R support. This means that notebooks can be authored using the R language. Built-in R support has been added for Spark R and Sparkly R. This makes it easy for data scientists to develop machine learning models using familiar interfaces with the R language. R can be used both from notebooks and Spark job definitions. Now that you've gotten an overview of what's included in the first release of data science in Microsoft Fabric, let's take a look at some upcoming experiences. We have a lot on our roadmap. What I will cover next is not everything, but it's some of the highlights. As a continuation of some of the features Misha covered earlier, we will be introducing support for hyperparameter tuning powered by Flamel. Flamel is a package to help automatically find accurate machine learning models at low computational cost. It frees data scientists from worrying about hyperparameter tuning and model selection, and this will help optimizing ML model development. And since we use Flamel for hyperparameter tuning, we will also introduce support for AutoML with Flamel. This allows you to automate building ML models. This will be a code experience to start with, and you will be able to use it from notebooks. And the best part is, it's integrated with the built-in MLflow tracking in Fabric. Another new capability in Fabric, which we are really excited to share more about, is Semantic Link, which offers a powerful toolset to bridge data science and BI. Today, there are limited tools available for data science users using Python to tap into the semantic data layer. This layer contains many key definitions and business logic, and this is very relevant for understanding and exploring data. Semantic Link helps data exploration, the featureization process, as well as finding the right data for developing ML models. With Semantic Link, notebook users can explore Power BI datasets from Python and Spark SQL, and this includes exploring things like tables, calculated columns, but also things like measures. Users can explore and query and validate the data in Power BI datasets directly from notebooks. Let's take a look at a demo of Semantic Link. A data analyst has collected sales data in Power BI and built out some reports for the business. She realizes that she could use better revenue forecasting data and wants to collaborate with a data scientist. Thanks to Semantic Link, data scientists can now tap into the Power BI semantic data model and business logic, and leverage that to quickly get a better understanding of the data in order to answer business questions and solve problems using machine learning tools. Semantic Link offers a Python library called SemPy that helps data scientists and other Python users to access, explore, and validate the Power BI semantic data layer. This layer contains things like tables and applied calculations and logic like calculated columns and measures. With SemPy, all of this can be accessed using tools that data scientists are familiar with, like Python. In this notebook, we're using Semantic Link and SemPy to browse a given Power BI dataset. But first, we can list the datasets we have access to. We can pick one from the list and start querying the data. As we're reading and querying the data, we're working on a snapshot of the dataset, and the results get saved in a semantically aware pandas data frame. We can visualize the relationships between the tables right here from a notebook cell. We can also list available measures in the dataset. For each measure, you can see details like measure names, measure expressions, and data types. This is a great way for data scientists to read these values, but also to understand the logic and formulas behind these measures. SemPy also allows us to read the content in tables and the measure values using built-in APIs. But there is more. Semantic Link also lets you query the Power BI dataset, including measures, with Spark SQL directly from notebooks. Now that a data scientist can easily query and explore the semantic layer from a data frame, it also means that it's much easier to use Python libraries to explore the data. To build a forecasting model, we're going to use Prophet, a popular time series forecasting library. This allows us to build a machine learning model to forecast future revenue. And the training data comes from the Power BI dataset. The forecasted values are written to a delta table in the lakehouse. And thanks to the direct lake mode, we can now seamlessly make them available for Power BI reporting. With Semantic Link in Microsoft Fabric, we are really excited to bridge data science and BI. We're also adding an integration with Cognitive Services pre-built AI models in Microsoft Fabric. This means that users will be able to access models for text analytics, anomaly detection, text translator, and more out of the box without the need to pre-provision any resources in Azure. We will start to offer these experiences from code APIs, but evolve them to more UI-based experiences. And there's a lot more we want to offer using built-in AI. Thanks to integrating with Cognitive Services, it means that we can also offer built-in integration with Azure OpenAI. We will bring developers in Microsoft Fabric a large set of productivity-boosting experiences. For notebook users, this means that we will offer built-in Copilot experiences for generating code, explaining code, troubleshooting, and much more. We're using the best-of-breed AI models from Azure OpenAI and contextualizing our interactions to be relevant for your data and your code. This wraps up our roadmap section. We hope this session was useful and gave you a good overview of data science in Microsoft Fabric today, but also what lies ahead. If you're curious and want to learn more, here are some links to get you started. If any of the roadmap features caught your attention, you can also sign up for private previews as they become available. We appreciate that you took time to watch this session. Thank you.